So last time we were talking about the binomial distribution, the binomial random variable, and how to calculate some probabilities using the formula and using the function on the calculator. To wrap up the discussion of binomial, let's talk about the mean and the variance of a binomial random variable. If you took our formula that we had earlier for the mean of any random variable and we plug in our probability for a binomial random variable, then you get this ugly looking formula. And it's not trivial to prove mathematically, but you can show that all of this summation just comes out to be n times p, which intuitively makes a little bit of sense because how many successes do you expect? That should be the probability of success times the number of trials. In our simple little example, we had flipping a coin, we had 3 trials and the probability of success was 0.4, so the mean should be 1.2, and that's exactly what we got from calculating the mean. So if we know that a random variable is a binomial random variable, then we have a very tremendous shortcut for finding the mean. If we do something similar with the variance formula, and instead of this generic probability, if we plug in our probability for binomial, we get another kind of ugly looking summation, but it turns out that the summation just turns out to be n times p times 1 minus p. The probability, the number of trials times the probability of success times the probability of failure. And if we plug in our numbers from the coin flipping example, we would have 3 times 0.4 times 1 minus 0.4, which is 0.72, which is exactly what we obtained earlier from using the variance formula. So to recap, the formulas related to binomial random variable, we have the probability formula, which is also on the calculator. We have a quick formula for the mean and a quick formula for the variance. And if you wrap that up in the square root sign, then we have a formula for the standard deviation. And these formulas might come up in later topics because there's other distributions that resemble the binomial probability distribution. Now, changing gears a little bit, a similar random variable is the hypergeometric random variable. Suppose I have a bag of 29 M&Ms, of which 8 are green. And we'll call those green ones successes. If I select a sample of 6 M&Ms at random without replacement, what is the probability that 2 of them are green? So this has some things in common with binomial because we're selecting a fixed number of items, n, and we're looking at successes. But the difference is in our coin flipping example, which was binomial, the coin is never going to run out of heads. So the probability of heads will be 0.4 for every single trial. But in this situation, the probability of a green M&M changes every time you select an M&M. So that is going to lead us to a slightly different formula for probability. So, and there's a lot of letters in this formula. Capital N is the total number of things in the population. So in this case, the total number of M&Ms. Capital M is the total number of successes in the population. So in this case, that's 8 because there's 8 green ones. Lowercase n is the number that you're selecting in your sample from the population. So in this case, that's 6. And then X, of course, is counting successes. So X is going to be the number of successes in our sample of n M&Ms. So this variable X is called a hypergeometric random variable, and the probability of observing X successes is given by this formula, which involves 3 different combinations calculations. But it's really not as ugly as it looks. There's 3 parts to this. There's 3 parts to this formula. If you're getting X successes, then that means out of the M successes in the population, you got to choose X of them. And then if you've had X successes, then you've had N minus X failures. And in the population, there's N minus M failures. So out of the failures or non-successes in the population, you have to choose N minus X of them. And then overall, the total number of things that can happen is the total number of items in the population divided by the number of items you're selecting for your sample. So this is all done with combinations. In our M&Ms example, the population size is 29. The number of successes in the population is 8. The number of M&Ms in our sample is 6, and the number of successes we want to know the probability of is 2. So we plug all those numbers into the formula and do some combinations on our calculator. So we have this. Okay, let's do this. So from the 8 successes in our population, we're choosing 2. And from the 21 non-successes, we're choosing 4. So that's a total of 6 being chosen, 2 successes, 4 non-successes. And the denominator is the total number of items in the population. Choose how many we're selecting for our sample. Notice this 8 and this 21 add up to 29. This 2 and this 4 add up to 6. That should always be the case in this formula. 3, 5, 2, 8. So our probability is 3, 5, 2, 8. And if I use this formula repeatedly, I can build the probability distribution table for X. And honestly, the only reason why I'm doing that is I just want to check that the probabilities add up to 1. So I just wanted to add up all those probabilities and double check that the probabilities add up to 1. Then the next question that comes up is, how many green M&Ms should I expect when selecting 6 M&Ms out of the bag? So in other words, what is the mean of this random variable? Well, not surprisingly, it's the sample size times the proportion of samples in the population times the proportion of successes in the population. So our sample size 6 times 8 over 29 is 1.655. And we can also check that on the calculator. I put, just so I could check this, I put the possible values of successes here and the probabilities here. And so I can do a little, hold on, I can do a little math on these items. List 1 times list 2. And so the mean is 1.655, which is coming right out of that formula there. The formula for variance for hypergeometric is very ugly, but just for the sake of completeness, there it is. So the variance for our selection of M&Ms out of the bag, our variance for the number of greens observed is about 1. We can use this to return to our problem that we did in the previous chapter about aces. Remember, we had a problem where we were selecting two cards out of the deck, and we wanted to know the probability that they're both aces. So n equals 52 cards total. M equals 4 aces in the deck. Lowercase n is 2 because I'm selecting 2 cards. And then x is 2 because I want to know what's the probability that both of those 2 cards are aces. You plug that into our hypergeometric formula, and you get 0.0045, which is exactly what we got in the previous chapter for that probability. But what's interesting is we can now easily extend this to other problems. What if I select 5 cards from the deck, and I want to know the probability that I get 2 aces? So now, of the 4 aces, I need to choose 2. Of the 48 non-aces, I need to choose 3. And then the denominator is, out of 52 cards, I'm choosing 5. So that all comes out to be about a 4% chance of getting 2 aces when 5 cards are selected at random out of the deck. The last random variable that we're going to talk about is the Poisson random variable. And the Poisson random variable comes about when successes are happening at a certain rate of time, usually involving time. Instead of successes happening in a given number of trials or in a given sample size, successes are happening at a certain rate. If our random variable x is counting the number of successes in a certain period of time, then x is a Poisson random variable. For example, suppose professors in the Department of Mathematics and Statistics cancel office hours at a rate of 10 cancellations per week. What is the probability that in a randomly selected week, we will observe 15 cancellations? So here's the formula for probabilities for Poisson. And it involves the rate at which successes are occurring, lambda to the x power, e to the negative lambda over x factorial. And oftentimes instead of lambda, you see mu as the parameter because lambda is the average rate at which successes are happening. So lambda is actually our average, which is why oftentimes it's just put in as mu instead of lambda. So in our example, the average rate of successes or cancellations is 10, and we're looking for the probability of 15 successes. So lambda to the x, e to the negative lambda over x factorial, 0.0347, and the Poisson formula is built into our calculator. Hypergeometric sadly is not, but Poisson is. We put in lambda, we put in the value for x, and that's all we need. And there's our probability of 0.0347. Of course, we don't need to have this calculator. You can do lambda to the power x, and then times e to the power negative lambda, and then divide the whole thing by x factorial. You can do this on any scientific calculator, and you should end up with the exact same answer. So that's the Poisson random variable, and that's it for chapter 3.